Because of extreme workload, I was unable to upload any video for the last 2 weeks. So in today's video, I am going to discuss about few problems taken from the book of Abstract and Linear Algebra by S.K.Mapa. For your convenience, you can see I have written all the questions and also along with their solutions. So let us start our class. So in the first question, it is mentioned here, suppose the group G comma naught is abelian. Abelian means we all know the structure is commutative. That means A naught B should be equal to B naught A, and it should be true for all A comma B belonging to G. If and only if A naught B whole inverse can be written in the form of A inverse not B inverse, and that must be true for all A comma B belonging to G. Now here you can understand, if we want to choose any two elements A and B taken from G, then as per given condition we can write that is A naught B whole inverse should be equal to A inverse not B inverse. Now A naught B whole inverse, just consider this one as usual, but from the right hand side using the property of inverse, what can you say? A inverse not B inverse is actually equal to what? B naught A whole inverse. Now again, if we want to take inverse on either side, then you will get what? A naught B inverse whole inverse. Similarly on the right hand side, B naught A whole inverse. Then again we have taken whole inverse over that expression. So technically we have obtained on the left hand side A naught B, and obviously on the right hand side we have obtained B naught A. So we can say A naught B is equals to B naught A, and this must be true for all A comma B belonging to G, and hence this is nothing but the property of commutativity. So we can say G comma naught is a commutative or abelian group. So this is the first part. Now conversely, you can assume that G comma naught is abelian. Abelian means commutative, so you must have A naught B is equals to B naught A, and obviously in the side note you can say for all A comma B belonging to G the result is true. Again you want to take inverse on either side, so that on the left hand side you will get what? A naught B whole inverse. On the right hand side you will get B naught A whole inverse. So A naught B whole inverse, no need to change the left hand side, but on the right hand side using the property of inverse you can definitely get A inverse not B inverse, and thus you have seen if this condition is true then the group must be abelian. Conversely, if the group is abelian then this condition must be true. So this is the proof of the first problem. Now moving on to the second one. In the second question you can see I have written proof that the set of all complex numbers of unit modulus. Unit modulus means if I want to choose mod z, that should be equal to 1, where z is certain complex quantity, then this particular set should form a commutative group with respect to multiplication. Multiplication means usual multiplication. Now say capital Z be the set of all possible complex numbers. We can choose any two arbitrary quantities small z1 and small z2 taken from capital Z. You can see I have used polar coordinate, polar form, obviously modulus amplitude form or polar form, you whatever you say. Now here you can understand in general Z should be written in the form of r cos theta plus I sin theta, where r is supposed to be the modulus of this complex number and theta is known as amplitude. Because it is mentioned here in the question, the structure should contain complex number of unit modulus, that means r should be equal to 1. So that's why you can see I have modified the structure of Z1 as what? Cos theta 1 plus I sin theta 1. There is no r because r is equal to 1 in this case. Similarly Z2 will be what? Cos theta 2 plus I sin theta 2. Now Z1 and Z2, both of them are belonging to capital Z. Now as per our criteria, we can say mod of Z1 and mod of Z2 should be equal to 1. Again remember the property of modulus. If we consider Z equals to r cos theta plus I into r sin theta, then what can you say about Z? It should be r square within bracket cos square theta plus sin square theta. Now here we can write mod of Z1 and mod of Z2, both of them are equal to what? 1. Now simply find out their product. That means you want to calculate Z1 Z2. Why? Because we need to verify the closure property. So cos theta 1, then I sin theta 2, cos theta 1 cos theta 2, then I sin theta 1 cos theta 2, and I square sin theta 1 sin theta 2. That means you will get, if you take the product of these two, cos theta 1 cos theta 2, then if we separate the real and imaginary portions, then I square, that is minus 1, sin theta 1 sin theta 2, this is the real portion, and then you will get sin theta 1 cos theta 2, then obviously you get cos theta 1 sin theta 2. So that's why directly I have written z1 z2 is equal to what? Cos of theta 1 plus theta 2 and I sin theta 1 plus theta 2 using the property of compound angle. So mod of z1 z2, what will be the value of this one? Just use the property of modulus, root over r square cos square theta plus sin square theta. But there is no r, so it will be root over cos square of theta 1 plus theta 2 plus sin square of theta 1 plus theta 2. And so that you can say this part is trivially 1 because cos square theta plus sin square theta is also 1. So mod z1 z2 is also 1. That means whenever mod z1 is 1, mod z2 is 1, where z1 and z2 are complex valued structures, mod z1 z2 is also 1. Hence you can say it is also a part of capital Z. So that means you can say closure property is satisfied whenever you are choosing this type of set. Now next you have to verify associativity. So that's why you can see in the next part I have written multiplication of complex numbers with respect to unit modulus. Obviously having unit modulus means it is given in the question, must be associative. Actually you can say this is hereditary property. Remember in the class I told you several times what is the meaning of hereditary property. The properties which hold trivially in a certain structure, in an algebraic structure to be specific, can be considered as a hereditary property. So here you can see the structure must be associative because we all know associativity for complex number is trivially true. So we have nothing to prove here, simply you can say associative property holds. Now we need to find out identity element. Simply we can assume 1 can be written as what? 1 plus I into 0. Now 1 plus I into 0, whenever we are multiplying this one with any other quantity, cos of theta 1 plus I sin of theta 1, you must say that should be equal to what? Cos theta 1 plus I sin theta 1, because practically although we are writing in the form of 1 plus I into 0, we are multiplying the actual quantity by 1. Similarly you can also say that this quantity can be written in the form of like this. You can write this one as cos theta 1, just a minute, you can write this one as cos of theta 1 plus I sin of theta 1 into 1 plus I into 0. Why I am writing this one? Because one stands for the left identity whereas the other stands for the right identity. So left and right both the identity element exist, and hence you can say 1 plus I into 0, that is simply 1, is nothing but the identity element for this structure. Now I hope you all remember this type of identity which is valid for the multiplicative operations is known as multiplicative identity. Now finally we have to find out the existence of inverse element. So let us take the help of conjugate complex number. Z1 is equals to cos of theta 1 plus I sin of theta 1. Definitely we can say this has been taken from capital Z. Now Z1 bar, conjugate of this quantity, that is cos theta 1 minus I sin theta 1. We claim it is also a part of capital Z. Why? Because we need to verify whether the modulus of this expression is 1 or not. Now you can see whenever you are checking the modulus of Z1 bar, it is also equivalent to cos square theta 1 plus sin square theta 1. So that is equal to 1. Now again multiply these two expressions, Z1 bar. Then you will get what? Cos square theta 1 plus I sin theta 1 cos theta 1 minus I sin theta 1 cos theta 1. That means I related portion will be cancelled, and finally you will get what? Minus I square, that is plus sin square theta 1. So ultimately Z1 bar should be equal to 1, which can be further assumed in the form of 1 plus I into 0, and hence you can say Z1 bar is the inverse element of Z1. So technically you can say inverse property is satisfied, because actually you can also say inverse axiom is satisfied, because for all possible Z1 belonging to capital Z, you have obtained its inverse. And finally, because it is mentioned in the question, you have to verify whether the given structure is a commutative group or not. So after considering all these structures, you can say capital Z forms a multiplicative group. And after this you can go for the verification of commutativity. So choose any two quantities Z1 and Z2. As mentioned earlier, take the product cos of theta 1 plus theta 2 plus I sin of theta 1 theta 2. Also you can choose z to z1, you will get the same result. So commutative property is also satisfied. And here you can say this property is true for all z1 comma z2 belonging to capital Z. And here also you have to mention z1 z2 belongs to capital Z. So finally you can say, although it is a group, it also satisfies the property of commutativity. Hence commutative group has been obtained by using the set of all possible complex numbers of unit modulus. So this is the proof of this result. Now in the next part you will see I have written this question already. I have explained this one in the class, so I am not writing here or explaining this one here, that G not be a group or relation rho is defined by A rho B if and only if B is equals to G not A not G inverse for some G in capital G. So rho is an equivalence relation. Remember, I have already discussed the solution of this problem in the class, so I am not discussing it here. Okay. Now moving on to the next one. This is again another problem taken from S.K.Mapa. Here you can see, let r theta shows the rotation of the point corresponding to shows the rotation of the points of the Cartesian plane about origin through an angle theta. Now rotation may be taken in the clockwise sense or even in the anti-clockwise sense. Depending on, you can consider it is either positive or negative. Now R is the set comprised of r theta type of elements where theta belonging to r, this is theta actually. Then we have to prove r comma star is a commutative group where star is defined as a composition such that r theta star r phi can be written as r of theta plus phi, where theta and phi both of them are members of capital R. So here first of all you can see, by default from this definition you can easily understand closure property is verified. Why? Because whenever you are choosing theta and phi from R, you can see r theta star r phi ultimately gives you what? R of theta plus phi. Now whenever you are choosing any two elements, particularly from theta, namely theta and phi from R, then definitely these two are the angles. Whenever you are adding two angles, you will get another new angle. So theta plus phi is definitely a part of R, and hence star must be closed because of this criteria. So we can say the structure R comma star is closed with respect to the given composition. Now I am considering another possible structure, r theta psi. You can consider these three elements are also taken from the set R. So r theta star r phi star r psi can be written as what? From the first two you can see r of theta plus phi is written. From the last part star r psi. From here on r of theta plus phi plus psi, which can be further rewritten as what? R theta star r of phi plus psi. Why? Because you can separate this expression. R of theta phi plus psi, you can separate this one, then r theta can be taken in front of this one. Again r of phi plus psi can be rewritten as what? R phi star r psi, because of this given composition. So you can see, whenever you have taken three arbitrary elements, still you are able to show that the given structure is associative, and this must be true for all possible elements belonging to R. So finally you can say this is true for r theta, r phi, r psi belonging to capital R. So associativity is also true whenever you are considering this type of composition. Now moving on to the next one. Obviously we need to find out the existence of identity element. We claim that r naught is the rotation of the points of the Cartesian plane, in the Cartesian plane. Actually you should write in the Cartesian plane about the angle or through an angle 0 degree. So whenever you are using this criteria, definitely you can say if this represents the rotation about 0 degree, so r naught star r theta must be equal to what? R theta. Similarly r theta star r naught, that is also equal to what? R theta. So both of them are members of R. So r naught must be the identity element. And finally, if theta rotates in the counterclockwise sense, then as per question we can say theta must be greater than 0. Actually anti-clockwise direction is considered to be the positive direction. Now let us consider the clockwise direction, by means of which we have defined an angle, namely theta dash. Now theta dash rotates in the clockwise sense, so you can consider if counterclockwise or anti-clockwise direction is supposed to be positive, then clockwise direction, because it is the opposite to that of counterclockwise direction, it should be considered as negative. So we can imagine we have chosen theta dash in such a way that theta dash may be equal to minus theta. So r theta star r theta dash, whenever we are considering this one, as per our construction we can write r of theta plus theta dash. But what is theta dash? Theta dash is minus theta, so r of theta minus theta, it should be equal to r naught. Because already we have shown r naught is the identity, then we have established the existence of inverse. And also intentionally you can mention r theta dash star r theta, that is also equals to minus of theta plus theta, that is r naught. And this is true for all possible r theta belonging to r, for all r theta belonging to r. So you can say r theta dash is the required inverse element of r theta. That means for each and every element belonging to r, inverse element exists. And finally, choosing any two arbitrary structures theta and phi from r, so then you can say r theta star r phi is also a part of what? R of theta plus phi, which can be written as what? R of phi plus theta, and further you can say this is equivalent to what? R phi star r theta. So commutative property is satisfied. So considering all these properties, you can say r comma star is a group. And just before the fifth property, you can say r comma star is a group. And after the proof of commutativity, you can say r comma star is a commutative group. So this is the proof of this result. Now this is another important problem. You can find this one in the exercise of RM Khan. Prove that the set of nth roots of unity. Nth roots of unity means, remember in class 11 you have seen cube roots of unity, that is omega cube, that is equal to 1. We have used this one, or simply sometimes we used to write x cube is equals to 1. X to the power 4 is equals to 1 will ultimately give you fourth root of unity. So similarly, if you want to find out nth root of unity, simply you can consider x to the power n equals to 1. So x will be what? 1 whole to the power 1 by n. Now suppose we are considering the set of nth roots of unity, then you have to prove it is nothing but a finite abelian cyclic group. Now I am not discussing about the meaning of cyclic group, because we are not discussing the properties of cyclic group so far, we are yet to discuss it. So simply I will focus on the proof regarding abelian property. That means I will show that the structure will satisfy commutativity. Obviously it will be a commutative group with respect to multiplicative operation or composition. Now 1 whole to the power 1 by n. First of all, we can consider this structure. Intentionally we can rewrite this expression as what? 1 plus 0 into I whole to the power 1 by n. So cos 0 plus I sin 0 whole to the power 1 by n. 1 can be written as cos 0, 0 can be written as sin 0, that's why. So cos 2r pi plus I sin 2r pi, we are using the general values where r is some integer. Now using de Moivre's theorem, we can say 2r pi by n plus I sin 2r pi by n. Remember, r must satisfy the criteria 0, 1, 2, dot 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 n minus 1. So here you can also write r is equals to 0, 1, 2, dot 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 n minus 1. Now this part can be written as what? E to the power 2r pi into I whole divided by n. Why? Because remember, e to the power I theta is what? Cos theta plus I sin theta. That's why we can use this notation. Now what you have to do, first of all, let us try to put r is equals to 0, 1, 2, 3 dot 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 n minus 1 in this structure, so that we are able to get the actual structures of the nth roots of unity. So if we consider G is the set of nth roots of unity, after putting r is equal to 0, you will get e to the power 0, that is 1. After putting r is equal to 1, you will get e to the power 2 pi I by n. After putting r is equals to 2, you will get